Hello everyone, welcome to MindSpan education. Last video we looked at gradient and Jacobians. If we have a function that takes input as a vector and produces some scalar as output, and if we are interested in finding the first derivative of this function, then we saw it is nothing but the gradient, and it will be a vector, right? If we have a function that takes input as a vector and produces output that is again a vector, and if we are interested in finding the first derivative of this kind of function, then we have found that it is nothing but the Jacobian. So Jacobian is a matrix. In this video we are going to look at Hessian. So Hessian is nothing but the second derivative of this kind of function. Okay, now let's try to look at what is Hessian. Let's suppose we have function that takes vector as an input from n-dimensional space and produces a scalar quantity, right? We have already seen that this gradient of this function f is nothing but the first derivative of this function, and it is not exactly first derivative, that the transpose of it, right? We have already seen in our previous lecture, right? Now let's think of this gradient of this function as a new function, right? So what is gradient? So gradient is nothing but it keeps all the information of the partial derivative, right? So let's suppose if we have this vector that is from n-dimensional space, that means it will have n component, x1, x2, x3 and xn n components, right? So you take the partial derivative of this function with respect to the first variable, and you take the partial derivative of this function with respect to the second variable, and you find the partial derivative of the function with respect to all the variable that you have, right? So this is what we call as a gradient, right? Now you can think of this gradient as a new function that takes the input x and produces this vector, right? So can I say that this gradient, if you think of this as a new function that takes the input from, in this case, n-dimensional space, that is this vector x, right, and gives you a vector that is in n-dimensional space, right? Now if I ask you what will be the first derivative of this kind of function, so we have seen in our last class that if we have a function that maps a vector as that takes vector as an input and produces another vector as output, then the first derivative of this kind of function is nothing but the Jacobian matrix. And what will be the size in this case? The size of the Jacobian will be n cross n, right? And the first derivative of this is nothing but the second derivative of this function f. So it is nothing but the f double dash x, right? And it is nothing but the, if I take the Jacobian of the gradient, so the Jacobian of the gradient is nothing, it will be the second derivative, and this is what we are calling it as a Hessian, right? So this Hessian is nothing in this case, it is just the Jacobian of the gradient, right? And we know that how to find the Jacobian matrix, right? So you can think of this as a function f1, and this as a function f2, and this as a function fn, right? And all those will have multiple variables, right? We will take an example, but let's try to find out the Hessian, that is nothing but the Jacobian of the gradient. So how do you find the Jacobian of the gradient? And that will be nothing but the Hessian, right? So you can think of this as a function 1. So just take this function. So this is the function, right? And what you will do, you will simply take the partial derivative of this function with respect to the variable, first variable, right? And again you will take the function, the same function, that is f1, and you will take the partial derivative of this function with another variable, right? Let me give some gap here, right? And so on you will do. You will take the partial derivative of this function with respect to all the variable. So you have n number of variable, right? Now what you will do, now you will take next this function and you will do the same thing. So now we have del f del 2, and you will do the partial derivative of this with respect to x1. You have this function, you will do the partial derivative of this function with respect to x2, right? And again you have this function, and you will take the partial derivative with respect to xn, right? You will do with all the variables. So here what is the function? We have this function del f divided by del f del n, and you will take the partial derivative with respect to the variable x1, right? And here you have the function that is del f del n, and you will do the partial derivative with respect to the nth variable, right? So what is this? What we have found? We have found the Jacobian of the gradient, and that is nothing but the Hessian. So Jacobian of the gradient would be the derivative of this function, right? And that is nothing but the second derivative of this function, and we have just seen that this second derivative is nothing but a matrix, and that matrix that we call is a Hessian matrix, right? So this can be written as, let me make it little bit small here. So this Hessian can be written as del square f del x1 del x1 del square f del xn del x1 del square f del xn del x1 del square f del xn del xn. So this is your Hessian matrix, and it is nothing but the second derivative of this kind of function, right? Let me take an example so that you have a clear idea here. So let's assume that we have a vector or input that belongs to some two-dimensional space. So it will have the two components. Let's suppose this x1 and x2, right? And let's suppose we have this function fx is equals to sine x1 plus x1 square x2 cube, right? So simply let's first find out what will be the gradient of this function. So the gradient of this function, so you just need to find the first derivative with respect to x1 and the partial derivative of this function with respect to variable x2, right? Now you just need to keep the other, when you are doing the partial derivative with respect to x1, you just need to keep the other variable fixed, right? So in that case, the partial derivative would be cos x1 plus 2x1 x2 cube, right? And now you are doing the partial derivative with respect to variable x2, so you can just keep other variable fixed. So here we will have the partial derivative, that is 3x1 square x2 square, right? So this is the first derivative, and first derivative is nothing but just the gradient, right? Now what you can do, you can simply, if in order to find the Hessian matrix, and that would be nothing but the double derivative of this function, and that is nothing but the first derivative of this gradient, and that is nothing but the Jacobian matrix, right? And how you find the Jacobian? So you look at this function as f1 and this function as f2. So just pick this function f1 and take the partial derivative with respect to all the variables. So let's first take this function and take the partial derivative with respect to variable x1, right? So in that case it will be minus sine x1 plus 2x2 cube, right? Now again you need to pick this function, since we have taken the partial derivative with respect to x1. Now next you need to take the partial derivative with respect to x2. So in that case you will have the 6x1 x2 square, right? Now take this function and take the partial derivative with respect to x1. So in that case it will be 6x1 x2 square, right? And take again this function, you have taken already partial derivative with respect to x1. Now you need to take the partial derivative with respect to x2. So that would be 6x1 square x2, right? So this is your Hessian matrix. And if you observe, the Hessian matrix is a symmetric matrix. So if you take the transpose of this matrix, you will get the same matrix. So Hessian matrix is symmetric. So Hessian matrix is a symmetric matrix. That means H is equals to H transpose. Alright, let's take one more example. Let's suppose if we have this function fx is equals to x transpose ax, and this a is again a constant matrix. That means it will have no effect if I change the x, right? And what will be the double derivative of this function, or in other words, what will be the Hessian of this function, right? And we have already seen the gradient of this function is nothing but a transpose plus a x, and if it is a symmetric, a is a symmetric matrix, then that would be 2ax, right? And now again if you take the derivative of this gradient, that is, and that would be nothing but the Hessian, or that is nothing but the double derivative of this function, right? And you can simply apply the product rule here, right? And it is a linear function, so the Hessian would be a transpose plus a, right? So that was the basic overview on the gradient, Jacobian and Hessian. It was just a overview of the matrix calculus. So if you would like to go into the details of this subject, so you will need to explore the matrix calculus in a very detailed manner, right? But I have given you the basic idea so that as you go on with the machine learning course, so that you do not have much difficulties while dealing with these kind of equations, right? So at least you should have the basic idea that in what way you should proceed, right? So there is a lot here that we can talk about. We can talk about the functions that takes matrix as an input and gives you a scalar quantity like the determinant of this matrix A. So we can even ask you what will be the first derivative or the gradient of this function A, right? Where it is equal to, so the function is that takes the input matrix as A and produces a scalar quantity, and this is the function that is the determinant of A, right? Similarly, we can have a function that the trace of matrix A, right? Or we might have the function that takes the input as a vector and produces as a matrix, that is upper triangular matrix, right? So we might have this kind of function, and we can ask what will be the derivative, second derivative of this kind of function, right? But let's not go into much detail of this matrix calculus. So if you would like to have to go into the details, you need to explore the matrix calculus, but we have the basic idea that we need to have as we proceed with the machine learning course, right? So let me give you one more result directly here that we might encounter, that the gradient of the determinant of this matrix A and log of the determinant of this matrix A, what will be the gradient of this? So what you have this matrix A, right? And you are finding the determinant of it, and you are taking the log of this matrix A and then finding the gradient of this. So that turns out to be A inverse, right? So you can take this as a direct result. Even you can think from the ordinary calculus that just to have the analogous analogy. So what's the differentiation of this log x? That we know 1 upon x. So you can think like this, that the first derivative of this log A, where A is a matrix, so that is nothing but the A inverse. Alright, so that was about the calculus. We have basic idea about the matrix calculus. Now I think we are good to go with the review of probability theory, and I will try to review this probability theory in one lecture, and that will be our next lecture. That is all. So